So this video is about the fundamental theorem of calculus, the FTOC. So we're going to start with just some function f prime of x that's continuous on a closed interval from a to b. If that's true, if it's continuous, then the integral from a to b of f prime of x dx equals f of b minus f of a. So if you take a look at what's happening, you're starting with f prime and we're doing the antiderivative to get to f. In fact, it looks like this. We'll say it's f of x. We'll say from a to b. And then we take our b and we'll plug it in, f of b minus f of a. And we'll look at that analytically a little later, but this is just really about understanding what this represents. So we're starting with some function, and what we're ending up with is a change in its antiderivative, but it's a change in a y value, really. So some people ask, why are we starting with a derivative? Well, I'm starting with a derivative because I wanted you to see the antiderivative easily. What some people start with is actually the integral from a to b of f of x dx because, hey, you're integrating some function from a to b. And then you have to go say, well, what does that equal? Well, I need the antiderivative of little f. So sometimes they'll write that as big F. So it's big F of x from a to b, but that's not really a mathematical symbol there, which is why I like to stick with this one. But they'll do that. And then they'll say, so this equals f of b minus big F of a, where f is the antiderivative of little f, which these are both the same thing. So it doesn't really matter which way you look at it. What I'm more interested in is what does this actually mean for doing math and the different kinds of problems. So what you're looking at here is if you are integrating some function from a to b, and let's say this derivative, what you actually find is a net change in height. You have f of b minus f of a, so you are finding the change in height. If you want to think about it in terms of like, well, what did that mean when you look at this geometrically? It means that that area you found under this curve is the change in height. So that's one way. The other neat way to look at it is if I just find this value here, then I can find the area underneath the curve, which is pretty cool because before you were limited to geometric shapes and now you aren't. You're basically, it's anything that you can take the antiderivative of. If I want the area underneath the curve of f prime of x dx, or just, I'm sorry, underneath the curve of f prime of x from a to b, then as long as I can find the antiderivative, I can actually find that area. So it doesn't have to be made up of triangles, rectangles anymore. The other way that's really neat to think about is, let's say that we start with velocity. So I've got some velocity equation, and I integrate that velocity equation, and I'm going to do it with respect to time. And we'll do it from some t equals a to t equals b, then what this actually gives me is the change in position. The antiderivative of velocity would be position with respect to time from a to b, and that will be s of b minus s of a. And this is just the change in position. So now if all I know is the velocity, I can actually might be able to tell you how far something went over a certain time interval, which is pretty cool. All right, so some real-world application problems just to look at. If w prime of t is the rate of growth of a child in pounds per year, so note you're starting with a rate, what does the integral from 5 to 10 of w prime of t dt represent? Well, because this is a dt, this has to be some function of t, but these are also t values. So we're starting at t equals 5, and we're going to t equals 10. So you come up here and say, what's t measured in? Well, it's our time, because w prime of t is rate of growth of a child in pounds per year. We're going to say our t is in years. So this represents something from when the child was 5 years old to 10 years old. So I could say, hey, this is w of t from t equals 5 to t equals 10. So that would be w of 10 minus w of 5. If W prime of t is pounds per year, then W is pounds. And we'll look at that in just a second. But this is how much the child weighed at year 10, taking away how much the child weighed at year 5. So what this will represent is the amount of weight gained by the child, and I should say gained in pounds, from year 5 to year 10, or from when he was 5 years old to when he was 10 years old. One way to look at units would just to be really look at this integral. So you have W prime of t dt. W prime is pounds per year. My dt is years. Those cancel out. That leaves me with pounds. Okay, another example. If oil leaks from a tank at a rate of R of t gallons per minute, so if we look at this, this is gallons per minute. Our dt is going to be in minutes. Okay, at gallons per minute at time t. What does the integral from 0 to 120 of R of t dt represent? Well, if I look at my units, I know it's going to have something to do with gallons. But I should also know that because if I start with a gallons per minute and I'm doing the antiderivative, I'm getting rid of a rate of change, so I'm left with something in gallons. Well, gallons from when to when? This is from time 0 to time 120. If I look at this, my time is measured in minutes, so from 0 to 120 minutes, or over the first 2 hours. Either set of units would be fine. But it would be, if you look, it'll be my amount of number of gallons at time 120 minus the number of gallons at time 0. And if we look at the context, the oil's leaking from a tank, leaking. So this would represent the amount, or let's say the number of gallons leaked from the tank over, and I could say the first 120 minutes or over the first 2 hours. And that would be fine. All right, one more scenario. A honeybee population starts with 100 bees and increases at a rate of n prime of t bees per week. What does this represent? Well, hopefully you see that this is going to be the net change in bees from time 0 to time 15. This represents our start amount. We started with 100 bees, and then we added in more bees. So what this represents is actually the total number of bees at the end of week 15. It's no longer a net change because we put in our start amount. Start plus net change will give us our final amount. So this is the net change from time 0 to time 15. So if we gained 35 bees in that time period, this whole thing represents how much we have at the end of the time period, 135 bees. So that's a beginning to look at exactly how this could be used.